This is section 4.2. We're going to talk about compound probabilities today. So it's not going to be the simple probabilities. We're going to do compound, independent, and mutually exclusive situation of conditional probabilities. First thing we're going to look at are independent events. Independent means they're completely separate. There's nothing holding them together. The occurrence and non-occurrence of one event does not change the other. If you look at your formula sheet on the very bottom, you're going to need to find that. You will see that the independent event multiplication rule simply means if you want A and B, you just multiply the two probabilities together. An example would be if you flipped a coin twice, the outcome of the first one does not affect the other, so they are independent. It's just a matter of multiplying them together. So heads on the first is 0.5, heads on the second is also 0.5, multiply them together. That's where you get your 2.25 when you multiply those two together. That's a simple idea of an independent event. Conditional probability means there's other things happening. There's going to be one's going to affect the other. These events are dependent upon each other. So notation, how it's noted, a couple different ways. Here's one way, probability of A given that B has happened. Or it might be actually written out, probability of A given that B has happened. And they can go A given B or B given A, depending upon which one's which. These formulas are also general multiplication rules. They're also in your formula sheet. It's the next one down. If it's probability of A and B, you could go probability of A times the probability of B given that A already happened, or vice versa. So there's a couple different ways to show it. This is how it's actually written, basically right in order. In your notes, you'll see this one and then these two in order. I just kind of talked about how to use them. You will multiply them together. The big deal is you got to determine, is it independent or is it a dependent event? So here's an example. I have two different examples. If you choose two cards from two separate decks, obviously that would be completely independent because you pulling a card from the first deck's not going to be pulling a card, not going to affect what you pull from the second deck. So this top example would be an independent event. So if it's independent, you can just multiply the first probability times the second probability in that order. So what's the probability of getting a 5 from the first deck? Well, there are 4 5s in the deck, and there are 52 cards in the deck. And then you just multiply, well, the second deck has the same probability, 4 5s and 52 cards. If you just multiply those two together, that's what your probability is of getting 2 5s from two separate decks. 1 out of 169 chances is what it would be for you to get that. You just multiply 113 times 113. Whereas the bottom one is a dependent event. Why is it dependent? Because when you choose two cards from the same deck without replacing the card, you are now changing your probability of the second draw. Now the first draw is going to be straightforward. You're not going to affect that. So if you look at your formula sheet, you notice that you have probability of A times the probability of B given A. Well, the probability of A just means what's the probability of pulling a 5 on the first card. That's not changing. It's still 4 out of 52. But now your probability of B, I know that's kind of sloppy, is changing. How is it changing? Well, 1 5 is already gone, and 1 card in your deck is already gone. So you only have 3 options out of 51 to get another 5. That's going to obviously make your odds a little bit worse. And if you go through the math, multiply straight across, and simplify down, you now have a 1 out of 221 chance compared to 169 with the independent decks or using the same deck. So that's kind of the option and the way that you use your formulas on your formula sheet. And versus or, it's a big discussion in this chapter, and it's kind of gets tricky sometimes. But and means that both of them must occur. Okay, both of them must occur. So here's a picture of both of them. They must occur. They're inside the Venn diagram where the circles overlap. Or means it could be one or the other. So in this particular case, it can be anywhere. Anything in your subset can happen as long as it happens in one or the other. Whereas we call an empty set, the probability if you go one or the other, one and the other, and it doesn't work. So that would be called an empty set. Intersection of A and B is empty because nothing overlaps. And we'll kind of see examples of that. So I just kind of talked about this. I just wanted to point out that here is some denotations. So if I want the probability of A or B, alright, that's the denotation, A or B. If it's A and B, that's this denotation down here. And that's when we're looking for the intersection of your Venn diagrams. So let's talk about mutually exclusive. Two events are mutually exclusive. They cannot, I repeat, cannot occur at the same time. We also call this disjoint. So basically the probability of A and B, if they are disjoint, since there's no intersection, it has to be 0. It can't happen. So addition rules. Here are some addition rules. They are on the very bottom of your page. So if they are mutually exclusive, which means they cannot occur together at all, you just need to add the probability of the first plus the probability of the second. If they are not mutually exclusive, which means they can occur at the same time, that means this overlap could count for both situations, so we need to subtract. So you basically got to ask yourself, can they occur at the same time? And if they can, then you subtract. That's the only difference between the two. And that's what I just said. Determine whether they're mutually exclusive, and then that'll determine what equation you will end up using with the two. Now, rolling a dice. Here's an example. What's the probability of a 4 or a 6? So what's your probability of getting either a 4 or a 6? Are they mutually exclusive? Yes, they are. You can't get one and get the other. That's what I ask myself. Can I get a 4 and a 6 rolling a dice at the same time? No chance. So that's the idea of, since they are mutually exclusive, that means you can go up and just add the two probabilities separately. Rolling a 4 is 1 out of 6 times. Rolling a 6 is 1 out of 6 times. Add them together. You get 2 out of 6, or 1/3. When choosing a card from an ordinary deck, what's the probability of getting a 5 or getting a red card? Are these mutually exclusive? That's what you have to ask yourself. No, they're not, because can you get a 5 and a red card? Yes, you can. You can get the 5 of hearts and or the 5 of diamonds. So there are options that they overlap or happen to both. So what's the probability of getting a 5? Still that 4 out of 52 that we've talked about. What's the probability of getting a red card? Red card can be any diamond or any heart. There's 26 of them in the deck out of 52. Now you must subtract any overlap, or the 5 and red card could show up. Okay, so the 5 of hearts and 5 of diamonds could show up in both spots. So that means you got to subtract 2 out of 52. That's why we get 4 plus 6 is 30, minus 2 is 28 over 52, or 7 out of 13. How about when choosing a card from a deck, what's the probability of getting a 5 or a 6? So if you're doing the or, okay, is it mutually exclusive? Can you get a 5 and a 6 in the same card? You should say no, which means it is mutually exclusive. Now I'm just showing you, you still can use this bottom equation, the one that stands for not mutually exclusive. It's just that you're going to subtract 0 out of 52, because you can't get a card that's a 5 and a 6. And then you just go 4 out of 52 plus 4 out of 52 is 8 out of 52. Reduces to 2 over 13. The last thing I'm going to talk about in this section is contingency tables. Responses to surveys basically can be put into tables. And then with these tables, you could ask a variety of questions that think about your conditional probabilities. So the first question I'm going to ask, if you look at the very bottom, is what's the probability that you have a male and a college graduate? Okay, so we got to figure out how many are males and college graduates out of our total number of people. Well, males, here's college graduate row, here's the male row. How many are there? 54 total. That's what we're looking for. Out of how many people? 187, because we're not sifting through, or we're not making any conditional things. So it's 54 out of 187. Let's go to the next problem. Male or a college graduate. So who can be a male or a college? And in this problem, when you have to look with the or, you got to decide, is this mutually exclusive? Can you be a male and a college graduate? Yes, because that's what we did on the very last page. So mutually exclusive, that talks about what's the probability of A plus the probability of B, and then you must subtract the probability of A and B. Okay, so how many are male? Well, how many males are there? There are 85 males, 85 out of the 187. Plus, what's the probability of a college graduate? Because this is event A, here's event B. College graduates, we have 116 out of the 187 college graduates. But we must subtract what I call the overlap. What individuals have been in both groups thus far? And that's what we talk about with the A and B. A and B in this problem is 54 of them are both in a male and a college graduate. So we're going to subtract that number. And then you need to just add those up. So 85, I'm actually grabbing a calculator, I don't want to do this in my head, plus 116 minus 54 equals 147 out of 187. That's your probability of being a male or a college graduate. Okay? So that's what we want to look for with that. Now here's the conditional part. I want to find out what's the probability of being male given you're a college graduate. Now what makes this tricky is you no longer have 187 as your total number. We are given that we're a college graduate. So what are we focusing in on? Only college graduates. All I care about is this row. Alright? And if I'm only focusing on this row, what's the probability of being male? Well, there's 54 males in the college graduate row. So it's 54, and instead of 187 total, we actually go up to the college graduate total. So there's 54 out of the 116. So that's the difference with the given. You just zero in, or you basically get rid of some of your information. You're zeroing in on being a college graduate, and then you're focusing on, okay, I want to figure out how many males there are. And that's the idea of using contingency tables, and you're going to see that in your homework. You'll also be tested on it. Today I want you to write, what should I have you write today? Math is still fun? No, let's not do that. Let's go Bison on a piece of paper to hand it to me to prove that you wrote the notes, and with your name so that I can tally them. Hope you have a great day.